Yes, let's start.
Yeah, I'm not seeing the screen in YouTube.
Yeah, it has come now.
Yes. Yeah, sure. Okay. Hello, everyone.
Yes, let's start.
Yeah, I'm not seeing the screen. Okay. Hello, everyone. Welcome to iitiansgateclasses classes. So today we will be seeing about propulsion part of the Gate Aerospace 2023 paper. So myself Akshay. So there were about 9 questions from core propulsion. So out of it, like 5 were 1 mark question and 4 were 2 mark question, totaling about 13 marks from the propulsion part. So let us see the questions. So question number 20 from the paper. So that is in a single spool aviation turbojet engine, which of the following is correct relationship between the total work output WT of a two-stage axial turbine and the total work required WC by a six-stage axial compressor, neglecting the losses. It's very interesting. So the first part we are going to see here is they have mentioned it's a single spool. Okay. Then they have also mentioned there is we can neglect the losses. So that means there is no mechanical transmission efficiency involved in between. So all we have to do is say like I have a turbojet engine. I have a compressor which is connected to a turbine which is driving the compressor, right? So now they have mentioned it's a single spool. So that means whatever work is delivered by the turbine, it is transmitted to the compressor through a single spool. So irrespective of the number of stages the compressor or the turbine has, so the work transfer is between the turbine unit to compressor unit. So this two-stage axial turbine or the six-stage axial compressor is just to make you confused. It is just transmitting work developed by the turbine unit. Say I have two turbines, but it's a single unit, right? So which is transmitted to a six-stage compressor. So it all together comprises a single unit. So it is just work developed. They are already mentioned. It is the total work output. That means a two-stage axial turbine, whatever it is developing, that is the total work output denoted at WT. And the total work required by the WC. So it means like all 6 stages together, what is the work required by the compressor? So option C should be correct. Work developed by the turbine, the total work is delivered to the total work required by the compressor, assuming there is no losses in between. So option C has to be correct. Okay. Let us move on to the next question. That is question number 21 from the paper. For a stage of 50% reaction, ideal axial flow compressor, symmetrical blading, select the correct statement from the given from the options given. Option A, they are saying stagnation enthalpy rise across the rotor is 50% of the rise across the stage. The static enthalpy rise across the rotor is 50% of the rise across the stage. Axial velocity component of the flow at the rotor exit is 50% of that at the rotor entry. The static pressure rise across the rotor is 50% of the rise across the stator. So out of this one we can straight away omit because it's an axial flow machine and ideal. So that means we are assuming it to be axial flow is constant. That is the main theme behind axial flow machines. So other than that, which option we can straight away omit is the option A, because they are saying stagnation enthalpy rise across the rotor, right? So rotor is the only place where you can have an energy transfer. If I want to change the stagnation condition, then I have to have an energy transfer. So in stator, there is only energy in transformation. There is no transfer of energy. So that is why there is no change in stagnation enthalpy. So this option is not correct because all of the 100% of the stagnation enthalpy rise occurs only in the rotor. Okay, irrespective of the degree of reaction, whether it is 50% or 100%. So this is going to be occurring only at the rotor. So now static enthalpy rise across the rotor is 50% and rise across this stage out of so yeah, this statement is correct because if I look at the degree of reaction, that is nothing but the static enthalpy rise in a rotor to a static enthalpy rise across the stage, right? So this is if R is 50%, so that means it is a 50% of overall static enthalpy rise in a stage. So this option is correct. The last option is also correct because static pressure rise across the rotor is 50% of the rise across the stator. Similarly, we can also define the degree of reaction in terms of static pressure rise in a rotor to static pressure rise in a stage. So from here again, we can conclude that the half of the static pressure rise occurs in a rotor. So this is also correct. Other half has to be coming from stator. Option B and D are correct. Okay. Let us move on to the next question. That is question number 22 from the paper. An aircraft is cruising with a forward speed VA and jet exhaust speed relative to the engine at the exit is Vj. If Vj by Va is 2, what is the propulsive efficiency? They are not exactly mentioned the kind of engine they are using in the aircraft. Let us assume it's a turbojet engine. So if it is a turbojet engine, so I have a incoming velocity. They have mentioned it as Va. So aircraft is cruising there. And the exhaust velocity, jet exhaust velocity, Vj. Right? So now it is producing the thrust, forward thrust, F. So if I define the propulsive efficiency of an engine, then I can define it as thrust power that is given by F dot Va divided by the propulsive power, that is M dot A times Vj square minus Va square. This is the propulsive power, right? So here I am actually assuming optimum condition. That means a thrust is produced only through a momentum thrust. There is no pressure thrust involved. Though it is not specified in the question, we can safely assume, right? So now
1 minute, Akshay. There is one concern.
Okay.
One person saying only option D wrong. Can you go back? Sorry to interrupt. Question number?
they're mentioning about 21, right?
Sorry. Yes. Question number 21, yes. So can you look
Yes.
back?
Yeah, option D is correct because the stage is compromised. So like let me draw the velocity triangle so I can go further. So
see, sir, read in the read the comment what someone saying. Rotor and stator is not status. Read the comment, sir, what it says.
okay, 1 second. I'm getting their point. static pressure rise
Option
across
D
the
is
rotor
rotor
is
and
50% of the
stator, sir, not
yeah,
stage. I think only,
yeah, that
some
is correct.
comment
That
is
is
there.
correct.
Please read in YouTube.
I got it. This is wrong because the statement they are saying 50% of the
Option
rise across the stator. Yes, sir, I can hear you. Yes, you can hear me, right? Yes, actually they are right. They are right. What they are suggesting, they are mentioned it is only across the stator. So when you compare across the stator, it is not 50% rise across the stator. It's actually 50% rise across the stator. Either if they are given the pressure rise across the rotor is 50% of the rise across the stage, or they could have mentioned it like 50% of the pressure rise occurs in the rotor and other 50% in the stator. So it is not mentioned in either way. So this statement is wrong. Actually, whoever mentioned it, they're right. Yeah, sorry from my end. Right? Okay. Okay. So let us move on to the next question. Yeah. So coming back to this question, I have a turbojet engine, say like assume a turbojet engine. So we can define a propulsive efficiency with an optimum expansion. So that is forward thrust power to the propulsive power. So thrust power can be written as mass flow rate of A times Cj minus Ci, sorry, Vj minus Va times Va divided by half mass flow rate of A times Vj square minus Va square. So now I can cancel out mass flow rate. So it turns out to be 2 times Va times Vj minus Va divided by Vj square minus Va square. I can write in terms of A plus B minus A minus B form. Right. So I can cancel this and this. So this comes out to be 2 times Va by Vj divided by 1 plus Va by Vj. So in the question they have mentioned Vj by Va is 2. That means Va by Vj is 1 by 2. So if I keep that one over here, so that becomes 2 into 1 by 2 divided by 1 plus 1 by 2, which is nothing but 2 by 3. So going to be 0.667. So it's a MCQ question. Option D is correct, 0.67. Okay. Now question number 28 from the paper. From the options given, select all that are true for turbofan engine with afterburners. Turning afterburner on increases specific fuel consumption. Turbofan engines with afterburners have variable area nozzles. Turning afterburner on decreases specific fuel consumption. Turning afterburner on increases stagnation pressure across the engine. Okay, so from the given statement, it was not sure whether it is equipped with a variable nozzle or not, but usually whenever we operate a engine with an afterburner, it's a constant area duct. At the end, we will be having a nozzle attached to it, right? So what we are doing, we are adding the fuel, right? So the moment when I add extra fuel to burn in the constant area duct, that means my specific fuel consumption is going to be increased. Though I am increasing the thrust, we define SFC in terms of mass flow rate of the fuel to thrust produced, but I'm adding more mass compared to the amount of thrust I am generating. So the ratio is going to be higher when I use the afterburner. So that is why SFC is going to be increased. That is one obvious observation. The other thing is what I am actually changing. So in gas turbine analysis, we assume the combustion process to be isobaric. That means constant pressure combustion. That is what we use in gas turbine engines. So that is why whether it is at the usual combustion chamber or at the afterburner, so we try to do a combustion at constant pressure. So the stagnation pressure is not going to be increased. In a worst case, it can decrease, but it is not going to increase. So in an ideal scenario, it is not going to change. So the stagnation pressure is not going to change. But because we are adding an energy in the form of fuel addition, so which carries some calorific value along with that, so the heat release will be m dot f times qcv. So that much of heat we are adding, so that is going to be resulting in the rise in stagnation temperature. So that means I had T naught 1 something like that. So after I'm using the afterburner on, so that is going to be T naught 2, which is greater than T naught 1. So that means what happens now? My mass flow rate will be get affected. So because mass flow rate is proportional to P naught divided by root T naught times A star. So to accommodate the change in mass flow rate, I have to change the area so that I can get an optimum expansion in all the conditions. So that is why, so variable nozzles are usually incorporated in the engines with afterburners. So this can be a right answer. So that is option A and option B. So this is not correct because stagnation pressure is not going to increase. In the worst case, it can decrease, but it stays same. So if option A is correct, then option C is going to be wrong, right? So option A and B are correct. Okay, let us move on to the 2 marks questions. So here I have 2 missiles A and B powered by a solid rocket motors have identical specific impulse, liftoff mass of 5,600 kg each, and burn duration of missile A is 30 seconds and missile B is 70 seconds respectively. The propellant mass flow rates for missile A and missile B for missiles A and B respectively are given by. So for missile A, they are given 120 kgs per second. Missile B, they are given 70 kgs per second. They are also given in the range of 0 to 30 seconds and 0 to 70 seconds. That means, so entire burn duration has the constant mass flow rate of the propellant. So that is fine. So neglecting gravity and aerodynamic losses, the relationship between the final velocities VA and VB of missiles A and B respectively is given by. So this question is fairly straightforward. So say I have missile A and missile B. Okay. So both of them have a identical lift-off mass. That means initial mass of A, which is also equal to initial mass of B, equal to 5,600 kgs, right? Then both of them have a same specific impulse. So specific impulse of A, which is also equal to specific impulse of B. So that is also given in the question. And for the missile A, the burn duration is 30 seconds, whereas missile B, the burn duration is 70 seconds. And this has a propellant mass flow rate of 120 kgs per second, whereas missile B has propellant mass flow rate of 70 kgs per second. So if I have a propellant mass flow rate and the burn duration, assuming a constant propellant mass flow rate for the duration of the burning, so that means I can write mass of the propellant which is carried by the engine A is mass flow rate of propellant in engine A times the burn duration in engine A. So that is nothing but 120 into 30. So that is going to be 12 3 is a 36, 3,600 kgs of fuel which is carrying. So similarly, mass of the propellant carried by the engine B is mass flow rate of the engine B times the burn duration in engine B. So that is again going to be 70 into 70. So that is 7 7 is a 49. So that is 4,900 kg of propellant which is carrying, right? So now I know the velocity change delta V from Tsiolkovsky rocket equation can be written as VE times ln of m naught by mf, right? So that means for engine A, VE can be written as ISA times G naught ln of m naught A divided by mf can again be written as m naught A minus MPA, right? Similarly, for engine B, I can write ISB G naught ln of m naught B divided by m naught B minus MPB. So now if I take a ratio of these two, delta VA divided by delta VB, that is going to be IS is same for both the engine. G naught is gravitational constant, so that is also same. So that get cancels. So I'm left with ln of m naught A divided by m naught A minus MPA whole divided by ln of m naught B divided by m naught B minus MPB, right? So now everything is known to us. So we can substitute the number. So that is 5,600 divided by 5,600 minus. So we got this 3,600. So that is going to be 2,000 divided by ln of 5,600 divided by 5,600 minus 4,900 going to be 700. So the ratio is going to be 0.495 is delta VA divided by delta VB. So now what is delta VA? Delta VA is nothing but V at the burnout in A minus V initial, right? So similarly, delta VB is also V at the burnout in engine B minus E initial. So in both the cases, it's lifting off from the surface. That is what we are assuming. So this is going to be 0. So this ratio is nothing but VA divided by VB, which is equal to 0.495, or VA is roughly 0.5 times VB. So if I look back the given option, option C is correct. Okay. So now we will move on to the next question. So in this question, they are given the equivalence ratio. The gas turbine combustor is burning a methane and the air at an equivalence ratio of 5 is equal to 0.5, where the equivalence ratio is defined as fuel to air ratio actual to fuel to air ratio stoichiometric, and the stoichiometric ratio of the mass flow rate of fuel to the mass flow rate of the air at stoichiometry, that they are just defining what F by A stoichiometry means. If the air mass flow rate is 20 kgs per second, then the mass flow rate of the methane. This is a quite straightforward question. 1 second. This is a bit straightforward question. Only thing we have to do here first is, so we have to find the stoichiometric air to fuel ratio, because what they are given equivalence ratio. Equivalence ratio is fuel to air ratio actual to fuel to air ratio stoichiometry, right? So now if I want to calculate mass flow rate of the methane, that is mass flow rate of the fuel, so that means I already know what is mass flow rate of air. So if I calculate what is F stoichiometry, then I can calculate what is F actual, right? So F actual is nothing but equivalence ratio times F stoichiometry. So once I calculate stoichiometric fuel to air ratio, I have equivalence ratio. So from there I can calculate F actual. So there I can easily say mass flow rate of the fuel or methane is nothing but mass flow rate of the air times this one, 5 into F stoichiometry, right? So now everything will be known. So the first thing we are going to do now is to calculate the stoichiometric fuel to air ratio of the methane which is burning with air, right? So what is the chemical formula of methane? That is CH4, right? Which is mixing with air. So air is compromising oxygen and nitrogen in the proportion of 21:79, right? Which gives me CO2 plus H2O plus nitrogen as it is. So now if I balance this equation, so I have one carbon, so one carbon dioxide and four hydrogen, so which can give me two water molecules. So now you see 2 2s are 4. This is balanced. So now I have 2O plus O2, that is 2 times O2. So if I multiply 2 over here, so my equation is now balanced. So 2 into 3.76, sorry, it's not 7.76. Right? So now my chemical balance is done. I can calculate fuel to air ratio in stoichiometry. So that is nothing but summation of number of molecules into molecular weight in the fuel to number of molecules into molecular weight of the air. So that means I have a molecular weight of the carbon, that is 12 times the number of moles of carbon I have is 1, plus molecular weight of the hydrogen times the number of moles of hydrogen is 4, divided by molecular weight of the oxygen. If I take O2, that is 32. So number of moles of O2 I have is 2, plus molecular weight of nitrogen N2 is 28 times number of this one I have 2 into 3.76. So if I calculate this one, I get F stoichiometry as 0.02914. So this is my F stoichiometry. So now I can calculate mass flow rate of the methane, that is fuel is F stoichiometry into equivalence ratio times mass flow rate of the air, right? So you just use all the numbers you have now, 2914 into 0.5. Sorry. F stoichiometry is coming out to be 0.05583. Okay, yeah, 0.0583 times 0.5 into 20 kgs per second of air. So that gives you around 0.583. kgs per second. So let us try to see. They are asked you to round off to 2 decimal places, so you can roughly keep 0.58 kgs per second. Okay, let us move on to the next question. That's again the 2-mark question. Question number 64 from the paper. A centrifugal air compressor has inlet root diameter of 0.25 meter and the outlet diameter of the impeller is 0.6 meter. The pressure ratio is 5. The air at the inlet of the rotor is 1 atmosphere and 25 degrees Celsius. The polytropic efficiency is 0.8 and the slip factor is 0.92. Use Cp is equal to 1004 joules per kg Kelvin and gamma is 1.4. The impeller speed in revolutions per minute is. This is again an interesting question. So what do we have is, I have a centrifugal compressor right, with the impeller root diameter given and impeller tip diameter is given. Right, so I am writing D2 as impeller tip diameter, D1 as root diameter. And also they are given air is entering with the condition 1 atmosphere and 25 degrees Celsius. So now what they are given, this compressor has a pressure ratio of 5, and we can use the properties of air gamma 1.4 and Cp as 1004 joules per kg Kelvin. And they are also given the polytropic efficiency of this compressor is going to be 0.8, right? All they are asking is the revolution per minute. So N RPM, right? They are also given the slip factor 0.92. What is slip factor? That is going to be CT2 divided by U2, right? That is given. So now you see this question very carefully. If I want to calculate the revolutions per minute, so that is related to the blade speed at the impeller tip. So I have a work done by the compressor can be written in terms of sigma times U square, that is at the impeller tip. So U can be written as pi d2 n divided by 60 whole square, where n is already in revolution per minute units, right? So which can also be written as Cp times delta T naught in the compressor, the rise in enthalpy in the compressor. All we have to do is sigma is known, D is known, Cp is known. I have to find out what is the stagnation temperature change across the impeller. So if I calculate that one, I can get the n value. So that's straightforward. So let me write it for n also. So n can be written in terms of square root of Cp delta T naught divided by sigma times $60 divided by pi times d2. So this is what we need to calculate n. So now we will try to find out how to calculate delta T naught. So we know efficiency of the compressor is nothing but T naught 2 dash minus T naught 1 divided by delta T naught, right? So this can also be written in terms of T naught 1 times pi c to the power of gamma minus 1 by gamma minus 1 divided by delta T naught. Also, I can write the same efficiency in terms using polytropic efficiency, that comes pi c to the power of gamma minus 1 by gamma minus 1 divided by to the power of gamma minus 1 divided by eta infinity c times gamma minus 1, right? So I can write this actual change in terms of polytropic process. So now if I compare this with this one, so what I can confirm is T naught 1 times pi c to the power of gamma minus 1 by gamma minus 1 divided by delta T naught, which is also equal to the power of gamma minus 1 by gamma minus 1 divided by gamma eta infinity c minus 1. So if I calculate this, cancel this and this out, so I can write it for delta T naught, that is equal to T naught 1 times to the power of gamma minus 1 by gamma times eta infinity c minus 1. So now everything is known to us. Put the values. T naught 1 is 298 Kelvin. So compressor pressure ratio 5 to the power of gamma 1.4. So it is 0.8 into 1.4 minus 1. So you will get something around 231.5 Kelvin as change in stagnation temperature. So you keep that back in the equation we just got it for rotational speed. So that is square root of Cp delta T naught divided by sigma into 60 by pi d2. So you keep all the number 1004, 231.5, 0.92, 60 pi, and d is 0.6 meters. So you will get revolution per minute as 998 point something 5. So they are asked you to keep nearest integer, round off to nearest integer, and round off to 15,999. Right? So this is the final answer. So you can also get something around 16,000. It is fine. Okay. So this completes all the questions from propulsion, but there is one more question. This question is there from the rocket propulsion. Let me just go through. This is more of a chemistry related question than the propulsion, but still we will try to solve it. Consider a cryogenic liquid rocket engine using an expander cycle with liquid hydrogen and liquid oxygen as the two propellants. The mass flow rate of hydrogen into the combustion chamber is 32 kgs per second, and the mass flow rate of oxygen into the chamber is such that mass flow rate of oxygen to hydrogen is 8. The combustion of hydrogen and oxygen is at stoichiometry. Assuming that the rate of the forward reaction is much larger than that of the reverse reaction, the rate of formation of H2O is. This is quite interesting question. So what do we have here is, so say I have a hydrogen tank and oxygen tank, so which are mixing together in the combustion chamber to do a combustion, H2 and O2. So if I do the chemical balance, what happens? H2 will mix with O2 to form H2O. So now balance is, there are one O, so there is O2 molecule. So to balance this one, if I have 2H2, then I can make 2H2O. So it is now balanced. So now you see the ratio. It is always going to be 2:1:2, right? So for every 2 hydrogen molecules, so when it combines with 1 oxygen molecules, I will get 2 molecules of water, right? So now we have to be much more careful, because now we have to deal with the molecular units. So that is moles. So how do we calculate number of moles? So that is calculated by the mass of the molecule divided by the molecular weight of the molecule, right? So now what is the number of moles of H2? H2O, that is mass of the H2O, that's the molecular mass, divided by molecular weight of the H2O. So first I have to calculate what is the molecular weight of the H2O. That is nothing but combination of hydrogen and oxygen. So molecular weight of the hydrogen is 1, and in one H2O I have 2 hydrogen plus 1 oxygen. Oxygen has molecular weight of 16, right? So this is a molecular weight of, that is usually in moles per gram or kilomoles per kg. Sorry, kg per kilomole. Right? So now, how many kgs of hydrogen we are using in the burning process? That is given in the question. We are using 32 kilograms of kgs per second actually hydrogen. So that means if I have 32, so if I have one hydrogen molecule, then I need 18. So I am going to get 18 kgs per kilomole of water. So what if I have 32 of such hydrogen molecules? So that means I have number of moles of H2O is going to be 32 kgs per second. So that's the mass of the hydrogen we are carrying divided by 18 kg per kilomole. So that is the amount of water I am going to get. That is going to be something around 1.778 or kilomole per second, or nearly rounding off to the integer value, that is 2 kilomoles per second. Okay. So now there is one more question actually, which I feel there is an insufficient data. Let us try to see this question. A supersonic vehicle powered by a ramjet engine is cruising at a speed of 1000 meters per second. The ramjet engine burns hydrogen in a subsonic combustor to produce the thrust. The heat of combustion for hydrogen is 120 megajoules per kg. The overall efficiency of the engine is eta naught, which is defined as the ratio of propulsive power to the total heat release in the combustor, and which is given as 40%. Taking acceleration due to gravity g naught is 10 meter per second square. The specific impulse of the engine is in second. So the question is straightforward in the sense like we have to find out the specific impulse. What is specific impulse? Specific impulse, we define it as the thrust per unit weight flow rate of the fuel. So that is mass flow rate of the fuel times g naught, right? So this is very straightforward to calculate, but here the question is how to calculate thrust. The thrust can be written in terms of, even if I assume it to be a optimum expansion, that is going to be Cj minus Ci, assuming F is very, very small, right? And what else is given? I have overall efficiency. They are defined it as the propulsive power to heat added. So they are given it to be 40%, right? So what is propulsive power? Propulsive power can be written as half m dot a times Cj square minus Ci square divided by heat added is mass flow rate of the fuel times the calorific value of the fuel. So calorific value of the fuel is given to you, that is 120 megajoules per kg. So this mass flow rate of air and mass flow rate of fuel together, I can write it to be F times QCV is Cj square minus Ci square, which is equal to 0.4. So the only problem here is both F as well as Cj are unknown. Ci is given, it is cruising at 1000 meters per second. So this is an unknown. So either I can express in terms of Cj or I can express in terms of F. In both the scenarios, it's going to be tough, because if I look back the IS, the specific impulse equation, that is going to be mass flow rate of A times Cj minus Ci divided by mass flow rate of the fuel times G naught, right? So this becomes Cj minus Ci divided by F times G naught. either I can express Cj in terms of all these variables or F in terms of all these variables. Both Cj and F are unknown to here. So we don't have any other way to calculate these two variables from the given information. So that kind of lacks with data. That's what I feel. I have to wait for the official key answer to confirm this. Okay. So yeah, other than that, like everything else is okay. I felt like it is bit tricky question paper, at least from the propulsion side. So there were many new type questions from those of the previous year questions compared to previous year question. It was really good challenging paper. Yes, you guys have any doubts? You can contact us, and thank you for attending this session.